All right, are there any questions from the last lecture? So today we're going to be talking about causality and propagators, right? So what are we doing in this section of the course? We started quantization of free theories, and we quantize a scalar field, real and complex. We pointed out the charge operator. We pointed out we did canonical quantization. We saw that how we talked about the structure of it is just basically a set of harmonic oscillators, and there's a measure on it. The measure is the covariant measure, ddk of 2 pi to the power of d 1 over 2 omega k, and then yeah, so we solved that theory. Well, we sort of started solving the theory that we solved the theory in canonical quantization in terms of A and A diagrams, right? So you know the algebra if you calculate the arbitrary point function, right? Everybody's good with that? We also did the same for the Dirac field, Dirac fermion. So 4-component vector. We talked about the symmetries that come up: charge, parity, and time reversal. We're going to talk about that in more detail today. So we're going to be talking about charge, parity, and time reversal, how they act on the spinor, on the Dirac field. And then we're going to end with some comments on causality and propagators. And that will wrap up this section. Okay? What we've achieved is just free field theory, scalar, quantization, I mean canonical quantization, in terminology you're familiar with, and spinor, the Dirac fermion. Last time I taught this course, next step was path integral quantization. So we would redo the quantization using path integrals, maintaining covariance, and we'll find like a lot more elegant and more appropriate for formulation of perturbation theory. So we're gonna do perturbation theory until the end of the course, Feynman diagrams. But this time around, I decided to add in an extra section, I guess, after today's lecture. We'll have 2 lectures to talk about other approaches to quantum field theory, not Lagrangian based. They're intimately tied to this. They're not just perpendicular. I'll have 1 lecture on Whiteman axioms. So you might hear these things. You might hear, actually, if you ever do quantum field theory, you hear a lot about Whiteman axioms and correlation functions. And the other one, there will be another lecture on algebras, local algebras of quantum field theory, which is another approach. So 1 lecture on each, and they're all related, right? So I'll try to take a perspective so that it's not too much of a leap. All right. But coming back to today's lecture, let's start with a summary of lecture 15. What did we do last time? We quantized the Dirac fermion in 3+1 dimensions. A Dirac spinor is a 4-dimensional representation. Here is the Dirac action. This is the Dirac mass. And this notation is somewhat compact. Psi bar is psi dagger gamma naught. And the Dirac matrices are these gamma matrices that satisfy this algebra, Dirac-Clifford algebra. And you recall how we constructed the representation theory of Lorentz group out of them, right? How was it? So we looked at the commutator of gamma matrices, and that was what we used to exponentiate to get the representations, right? Okay. So last time we saw that, well, this is a 4-component matrix, 4-component field. As usual, recall this notation. This is that covariant integral over modes, the on-shell condition, and positivity of energy. Then we had, it's a 4-dimensional vector. So 2 of them are here. These solve the Dirac equation, classical Dirac equation. These are other solutions to the classical Dirac equations. Each of them has 2 components, right? S is the up and down component. And the quantization goes this way. So that add a D dagger of S. S is a spin index up and down, and then B here. These are all the four components. These are particle, antiparticle, right? Then we saw that the anti-commutation relations are like this, right? So, of course, the components, these are this alpha and beta are the four component things, right? It's diagonal in that. And in space, the anti-commutator should be a Dirac delta function. These relations induce the standard anti-commutational fermionic anti-commutation relations that we discussed last time in the simple examples, right? All right, just a comment to come back to next time. The fermions, what's the dimensionality of the Hilbert space for that, say, B dagger K, B dagger up of K, B dagger of S of, oops, generates? Let's keep this to be up, two-dimensional. Now, let's say you have a discrete set of modes, right? Running over, for example, I don't know, if you quantize in a circle, some integer over R, right? What is the dimensionality of the Fock space that you get? Infinite, right? It's infinite dimensional because you have a discrete infinite number of modes. If you take the first mode, the dimension is 2. You take the second mode, there's another 2 times 2, 4-dimensional. 2 times 2 times 2, 3 of them. What is the Hilbert space that you obtain, or the Fock space you obtain if you tensor infinite number of 2-dimensional, countably infinite number of 2-dimensional vector spaces? You might not have noticed this, but that is uncountable. The resulting Hilbert space is, or vector space, is isomorphic. The dimensionality of it could not be labeled, could not be mapped to positive integers. It's continuum. That is part of the origin of the problems with quantum field theory. I'll leave that for you guys to think about. And of course, the case of bosonic modes is even much worse, right? Even when you do an infrared, this is an infrared cutoff, right? This is quantized on an finite volume. Another manifestation of UV divergences. So your Hilbert space is not just infinite dimensional, your Fock space is uncountably infinite dimensional, which is kind of sick. It's not sick. Doesn't it? Well, we'll talk about this next time. Unless anyone has a guess already how the solution comes about. In free field theory, it's okay. No, well, okay. All right. So using these anti-commuting creation annihilation operators, we wrote down what the Hamiltonian was. The Hamiltonian had an IR divergence, scales like V of space, and that comes from the anti-commutator of B of S K dagger and B of S of K, right? That has a delta of 0 in it. Because if this were K prime, you do delta of K minus K prime, and you pick the same mode, it's become delta of 0. The Fourier transform of which has an infinity in volume. So this is an infrared divergence. And then the UV divergence is the UV divergence. You recognize it, right? That's the cutoff in K that we're just talking about. The charge is just psi dagger psi. Notice that there's no time derivative in it. We commented on that before. This is nothing but the difference in the number of particles. It's the difference between the particle number and antiparticle number. Right? Good. So far, based on whatever I've said, it seems like quantum field theory suggests that for every particle, there could be an antiparticle. right? If you want to have the same number of them, then you have an extra symmetry, charge symmetry, but you don't have to. But we'll see today, hopefully, yeah, I think today, that it's a must. It's not that you could have it. Causality requires you to. That makes it a must. You can't have just particle and not the antiparticle. So causality, as usual, is a strong, very, very strong condition. We talked about P and T. We said that P is a unitary. These are Z2 symmetries. It's represented by unitary, and T, time reversal, is represented by an anti-unitary. Do you remember why that was? Because time reversal sends Hamiltonian to minus Hamiltonian, right? Hamiltonian generates del T. Time reversal generates minus del T. But because we want this to be a symmetry, it has to commute with e to the power of I h t. And the way to fix it is to assume that it's anti-unitary. Today, so we talked about C, P, and T as symmetries. We're going to talk about CPT acting on spinors and talk about causality and propagators. All right. So first thing that you notice is that how does P act on, so on a scalar field, so here's a scalar field, complex scalar field. How does C act? Phi dagger at the same point. Good? The action is simple. How does P act? Oh, sorry. Sorry. This is if these are four vectors, this would be P mu nu x nu, where P is the matrix 1. It only flips the space. How does T act? Well, you know how it acts. There will be a matrix T, which is nothing but, oops. If you recall, these are the Z2s that take you between the disconnected pieces of OD comma 1. All right. Now, today we're going to answer the question that, all right, this was a scalar field. How does C act on psi alpha of x? How does P act on psi alpha of x? And how does P act on psi alpha of x? I've already hinted at some of these transformations, but we're going to see them explicitly today. First thing to notice is that, of course, the action of this is going to be this T mu nu acting, so it's going to reverse the time for sure. But now, because it's a spin representation, there could be some, this is a 4 matrix, sorry, 4 vector. There could be a matrix sitting here, right, that acts on this index. So let me now write that and say there's a matrix here. Similarly, here we're going to have P mu nu, x nu, some matrix sitting here. And then similarly, it's going to be this sum. Now, this time around, it's just the same point. Right? But a matrix. What are these matrices? These are 4 by 4 matrices. What do you expect them to look like? They should be fixed by representation here. So what are they going to be? Exponential. Combination of gamma matrices. Those are the only 4 by 4 matrices that everything is made out of. Right? This is all fixed by representation theory. We're going to find this matrix, this matrix, in terms of gamma matrices. Right? Good. This is the first thing we're going to do in today's lecture. Then we're going to switch gears and talk about causality and propagators. And then in that case, I'll talk about only scalar. We'll go back to scalar. Any questions? Do you already have a guess as what is the principle that does this? By the way, I know that at this point, every other lecture I change my notation. So from now on, to make sure that everything is clean, I'll also give you two references so that you could pick your own notation. So section 3.6 of Peskin goes over this discussion. Then section 40 of Shrednicki also goes over this discussion. We have different notation, and you will now be surprised to know that my notation is different for today's lecture. All right. Yeah, so last time we talked about the particle hole symmetry, blah blah blah. But let's focus on the action of charge. Is this clear what I'm talking about, right? So these guys are unitary. This is a unitary in the Hilbert space. And this is the corresponding representation matrix, right? These are Z2, which means that C dagger, well, actually, yeah, C dagger is the same as C minus 1. So I can put it like that. Sometimes I write the minus 1, sometimes I don't. If you don't believe me, take the minus 1 of these. All right, good. This is an anti-unitary. But to answer this question, so first we're going to focus on C. To answer this question, we have to look at the origin of the charge symmetry. As opposed to the P and T, where I told you where it comes from very, very exclusively. It comes from the fact that the Lorentz group had 4 disconnected pieces and P and T were going between them. Charge is something that I really only motivated from this explicit transformation for complex scalar field. And at different points, I just said, oh, there's a symmetry that swaps the left movers and right movers. But let's be a little bit more specific about what it is. Notice that it does not, this action on the space is pretty trivial. The origin of that in representation theory could be traced to the following statement. Remember that at the end of all that song and dance of our representation theory, we said at the end of the day, we're going to build a representation by finding gamma matrices. That's satisfied. These are 4x4 matrices in 3+1 dimensions. That satisfy that Dirac Clifford algebra. You notice something, that if you pick gamma mu's that satisfy this algebra, if you take the transpose of them, they also satisfy this algebra. So there's a symmetry already at this level. This is the charge symmetry. This is the origin of it. As simple as that. This means, so our charge symmetry is some matrix C that when you take gamma mu, you sandwich it, it gives you back the transpose. Yeah.
Why does it, I mean, energy is just how transposing the gamma matrix tells us explicitly this gives you charge conjugation. Just from looking
there is a, when you pick your gamma matrices, you get a representation. That depends on gamma matrices. From the onset, you could have started with, given a set of gamma matrices and representation, you could have done the transpose of it. You would have gotten something else. But they're both equivalent representations. And then we just say there is a transformation that takes you from this to that. It could be a symmetry, your theory, or not. But this action is well defined, and that's what we're exploring. It turns out that it's often, in a lot of the theories, it's a symmetry. Not necessarily always, right? It's like P and T, right? There's no principle that tells you P and T must be symmetries. You write an action and you explore it. All right, so it's an operation that takes in, you sandwich the gamma mu with, and it gives you the transpose. All right, so what was gamma mu? Recall we basically wrote it down in terms of sigma mu and sigma mu bar. This is a 4x4 matrix. and sigma mu was identity Pauli matrices, identity sigma bar was identity minus. So you can already see what the transpose does. It swaps sigma and sigma bar. And if you recall, this was the issue of left-handed and right-handed, right? So it's the same symmetry we were talking about before. Swapping was left-handed to right-handed. All right, very good. So you just want to take gamma mu's, which are these guys, and see what is the matrix C that you should sandwich it so that you get the transpose. It turns out it's this matrix. It's minus I gamma naught gamma 2. What is that matrix? This is literally what the matrix is. And if you recall, at some point earlier, when I first introduced spinors, I introduced this like epsilon alpha beta and epsilon bar alpha dot beta dot that was raising and lowering indices in this abstract space. This is basically the charge operation. So when I was talking about, I said I was writing I don't remember what my notation was, but like some chi alpha, and I said, oh, I can raise this index using epsilon alpha beta, and that's a new spinor. That is the charge that is this spinor after the operation of charge. Spinor was an irreducible representation. After the action of charge is still an irreducible representation because it's a symmetry of the gamma matrices. Good. All right. So now the question comes up immediately: is the Dirac action invariant under charge symmetry? As a matter of fact, you know what? What I'm gonna do is this. I'm gonna leave it to you guys to decide how, using the action of charge on the Dirac. Well, actually, is it invariant or not? What's the answer? Yes. Any other? When would it be invariant? What is the symmetry? It swaps the left movers and right movers, right? If you recall, when we built the Dirac action, if we set the mass equal to 0, it's just a left mover and right mover. And now without the mass term, it's invariant under charge. So I just took the part of the action that doesn't have the mass term, and that's invariant. Now, from that, I'm going to deduce the action of C, right? Because this is psi dagger gamma naught, that's psi bar, right? Gamma mu del mu psi. Is that good? Everybody's with me? All right. So I'm going to put C's in the middle all over the place. You know this term, right? That's just given. This term and this term are related. How are they related? One of them is the dagger of the other one, because C is equal to its dagger, right? So from the invariance of this and the fact that I know this relation, notice that gamma 0 is invariant, right? Because gamma 0 has just identity. So it's transpose invariant. So I can just really move it around. If I want to switch gamma's, okay. From this, you can deduce that the action of it is like this. It sends psi to minus I gamma naught, gamma 2, psi bar transpose. What is psi bar transpose? Well, what is psi bars? Psi dagger gamma naught, you take the transpose of it. The transpose of gamma naught is gamma naught. The transpose of the dagger is psi star. Good? So I can write it in different ways. My notation has an extra minus sign compared to normal human beings. I think it's a stupid, well, I did not say that. It's not a convenient minus sign. Like in my notation, this notation is not the most convenient. It was convenient for the calculation I was doing, but all right, good. So it's clear where there's you could fill in the in between the gap, but it's clear where it comes from, right? So if I want to switch gamma 0 and gamma naught, gamma 2. So gamma 0, gamma 2, how is it related to gamma 2, gamma 0?
See.
Huh?
See. I see.
Gamma 0, gamma 2 is equal to,
Yeah.
it's negative of it. Because why? Remember the Dirac algebra. This tells you that gamma 0, gamma 2, if you switch them, you pick a minus sign. So, what? There's no magic to this. It's just a couple of lines of algebra to everything. All right. Now, the action of this transformation, you know the expression for psi, the canonical quantization. You could trace how it acts on B and D. It sends B to D and D to B. So it solves creation and annihilation. It solves the particle antiparticle, as we promised. So when it acts on psi, which was B and D dagger, it sends it to D and B dagger. Good. So when is a field, a fermion field, a Dirac field, invariant under chart symmetry?
Yes.
No. In this expression, look at this. These were solutions. These were solutions to Dirac equation, right? These are matrices. These are vectors, right? So it is invariant if your U is gamma gamma bar. Well, U is always gamma gamma bar. V is gamma. C bar, C prime bar. If you have this, then your equation is invariant. It's not that massless Dirac. Well, okay, I leave it to you guys to figure out, right? I think you can fill in the line of the algebra. If it's charge invariant, what kind of spinner is it? What do we call it? No. What kind of spinners do you guys know? There are only three. What's Myron? Thank you. Dirac was only Weil was only left-handed or right-handed, right? Majorana was the one that the right-handed was determined from the left-handed. How? Charge symmetry, charge invariance, right? And then Dirac was that you add arbitrarily, you take them to be arbitrary, right? So now with this condition, you're describing Majorana. Recall, like again, Majorana is a special type of Dirac that has the symmetry. It won't click until you do calculations. Just from experience, I can tell you that. All right. So what did we find? We found the answer to this. We found that this is minus I gamma naught gamma 2 star. I think in my notation there's another gamma naught here. I think this is Schrödinger's notation. Yeah, I think this is in my notation there's another gamma naught here. Because in my notation, this is this. Which is gamma star with which is psi star with gamma naught acting on the left. Good. So we found this matrix. What was this matrix? I just showed this to you guys. One minus one, right? Is that epsilon alpha beta epsilon dot epsilon alpha dot beta dot? And I think Schrödinger, that extra notation thing, the change is that it will have like this. Yeah, anyway, my notation, the good thing about it is that these are symmetric. Right? dimensions. I think, if I recall correctly, Shrednicki and Peskin both use the other notation. All right, so that is the transformation of charge. So hopefully now you know how charge acts. Good. Now, yeah.
So if you define the C operator this way, transpose the down matrix, how do you show C at a vector on the final?
This is not a spinner.
Yeah.
This is a scalar field. Right? It's a complex scalar.
So there's just two different definitions of scalar field.
Sorry, guys. You want to talk about charge symmetry, right? You have to ask the question of how does it act on one of your fields, on your EREPs. So it will take a different representation on each of your EREPs, right? If it's one-dimensional, real field, representation is one-dimensional. At most, it can just act with a constant, right? Whether for a scalar field, real scalar field, it acts trivially. Here, it's a two-dimensional. You could view this as a two-dimensional vector, and then you see what it does, right? You have to talk about the action of it on each representation. Why? Because it's defined at the level of the Dirac matrices. Take your favorite field. The mass is irrelevant to this game. Spin. You fix your spin. You first have to define an EREP in terms of gamma matrices. We talked about how to do that for spin half particles. Nothing fancy, right? But whatever it is, you write down an expression for it. Then what's your next step? No, come on.
So,
what did we just do? What was the next step that we did? We looked at the action, the free action. So take a particle of spin S, write down the free action for it. And now we could discuss the transformation properties. We could deduce the transformation properties from there. Yeah.
But so C, the charge conjugation matrix isn't, I mean, it depends on the representation.
There's no matrix. It's an operation. It's a unitary in the Hilbert space.
Yeah.
That is diagonal in representation through a Lorentz group. Acting on a scalar, it doesn't produce a spinner. So therefore, in each representation could be represented as a matrix of that representation. So you have to find it.
Oh.
You have to find it. It might act trivially. For example, real scalar field, in which case you don't talk about charge. Good? There we go. Remember, everything comes down to the representation theory, right? Okay. Now, the next step is P and T. Right? We define what P and T are, right? But not the action of them on the spinners. So we have to define what the right-hand side of this is. Right? So we're after these. All right, so what does parity do? It sends the x vector to minus x vector, which means that this, so there's a matrix beta here that we're gonna find. The matrix beta is going to be 4 by 4 and it's going to be related to Dirac matrices because we're talking about spin half representation. That's why it's 4 by 4. So how do we find this? The idea is to find a Lorentz invariant, a Lorentz scalar, or a Lorentz vector and deduce the properties from that. Last time, for C, I looked at the Lorentz scalar, which was that piece of the action, Lagrangian, right? So now we're gonna look at this. This is a Lorentz vector. Hopefully you recall this was a Lorentz vector. Good. Under parity, this is the time component of the Lorentz vector. It should not change. The spatial component of it should pick a minus sign. Oh. I'm sorry, guys. My handwriting is awful. This is psi, and this is psi bar. Right? So here is the vector. Oh no, 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 no. That was right. That was wrong. I was good. That was good. I was good. My bad. Yeah. So I how did I do this? No, 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 no. Well, all right. I don't remember. Whoops. I don't remember what is it that I was doing here. But all you need to do is you need to represent, oh my God, this action in terms of gamma matrices. And here's how it goes. I actually don't remember what this argument was about, but I think this was from this argument was deducing that beta is gamma naught. Let's stare at this for a second. Maybe I can recall how it works. So clearly, if I'm looking at how P acts on this, P acts on psi and gives you beta psi. So that term is good, right? Then P acts on gamma mu, right? And depending on whether, okay, yeah. This should be the transformation of the other one. There's a mistake here. I think the mistake is that this is bar and this is psi dagger. That would be sensible. Yeah, actually that is sensible, except that I have an extra gamma naught here. All right, I'll figure this out next time. From the transformation of the vector, you could deduce that this beta is gamma naught. So this is gamma naught. I think Schrödinger's notation, there's an I out there, extra I don't recall, or maybe Pascal's notation. But it's more, you could directly look at the action of it on psi. What does it do? It sends k to minus k, doesn't touch k, k naught. Right? And then it multiplies the whole thing by gamma naught. Here's your gamma naught. And you just have to take care of this k dependencies. After a change of variable, bringing this gamma naught inside to the both terms, you could arrange for, you could keep track of everything by flipping the sign of both of these, the k dependence here and here. So long story short, the action of it on the creation annihilation operators acts this way. It takes the particle, flips the k mode. So it takes the particle annihilation operator and creation operator. So P of B of K becomes B of minus K. But on the antiparticle, it flows the sign of this with an extra minus sign. So it treats the particle and antiparticle differently. So let's go back. What does C do? What was C doing? C was swapping B and D. That's all it did. No action on K. Swaps B and D. P sends B to B, particle to particle, antiparticle to antiparticle. Of course, the minus sign has to be there, right? Because it's acting in space. But it treats the particle and antiparticle asymmetrically, adding an extra sign. This extra sign is conventional, of course. It's a Z2 symmetry. You can put it here. This is where the notations, there are conventions that deviate from each other. This is my notation. Good. So now you could ask the following. What happens if you act with P followed by C? CP symmetry, CP transformation. Well, you know how it transforms, right? Finally, time reversal. So C, P, and T are the only discrete symmetries we're going to talk about this course. The time reversal is sends x naught to minus x, x naught to minus x naught, and it does not change x to vector. We said that it's an anti-unitary, it adds a minus sign to H. So there will be a matrix tau that sits there. A similar analysis that you can find in Peskin, and also this line of thing that I was trying to do here that I messed up. It's also in Peskin or Shrednik, your favorite textbook. This comes out to be minus gamma 1, gamma 3. All right. So how does T act? It acts minus gamma 1 minus gamma 3 with the sign of x flipped. That should surprise you guys. Exactly. So these calculations are non-trivial, right? Any guesses? Okay, this is might be misleading, right? Because this isn't canonical quantization. I'm not treating this already is not Lorentz covariant. I'm writing the field variable and some constant time slice or something. And it turns out that if when you do that, it's convenient to write this down. But where was it? This one? As the action. This is what's happening. So you write time reversal as parity followed by reversal of all the coordinates. And that acts non-trivially in spinners. You remember why? Hopefully you do. These are spinners, they pick up minus signs. Here, the reason that the time is not appearing is because I'm using a covariant, I'm on canonical quantization. So it's misleading. It's more convenient to write it in terms of the 4 vectors like this, like these guys. Then you would see it more manifestly, it's just flipping the tie. The reason I write it in this language is that I want to look at the action of it on the creation annihilation. This is a covariant, this is canonical quantization. On the creation annihilation operators for the particle and antiparticle. What T does is that it flips the sign of K and flips the spin for the particle. For the antiparticle, it does the same thing, but an extra minus sign for the antiparticle. Yeah.
In order to show this, because I recall that the creation and annihilation operators can be written as in terms of the field and the conjugate momentum at some constant time. That's right. So We could use that in order to show that with those relations, or is there any easier way to?
No, that's what we're doing. That's what we're doing. Yeah. That's exactly what we're doing, right? Here. You know what H is in terms of B and D's, right? All right. So putting all of this together, it tells you that if you take a psi of x, spinor of x, apply a CPT transformation, what it does is that it sends it to minus gamma 5. Remember what gamma 5 was? I gamma 0, gamma 1, gamma 2, gamma 3, gamma 4. Right, that was gamma 5. I defined it, right? I think I did. Psi star minus x. So here's a claim. Go check this. This is a symmetry of any local quantum field theories you know, right? Just check all the actions we've written down. And furthermore, I claim this is a symmetry of any local quantum field theory. With particles, without particles, I don't care. This is a symmetry of in 3+1 dimensions. There's a proof of it in 3+1 dimensions. Yeah.
What do you see here? Without any.
It's not a symmetry, so. I'm saying any local quantum field theory. What does that tell you? What does that tell you that CPT is a symmetry? What is PT? This, right? CPT being a symmetry tells you that when you apply this transformation, this is equivalent to charge transformation. That's what it says. This is the same thing as charge.
That's a concept time reversed, mirror flipped, charge reversed, universe is exactly the same thing.
3+1 dimensions, yes. Yeah. In all even dimensions, there's a proof. I don't know what the status of it is in even odd space-time dimensions. Maybe there's a proof, maybe there's not, but there's another symmetry I know that's true, which is CRT. That's the one that it makes some people mad that I say this, but our generation cares more about CRT than CPT, and they're the same thing in 3+1. Any questions? We're going to be changing gears. So this is the end of the story of CPT. And I apologize if I messed up the calculation up there. I don't know what I was writing over there, but it's line by line in Peskin or in Shredniki. Section 40 or 3.6.
So is there a way to distinguish between charge and?
No. Well, it depends what you mean by distinguish between them.
That's true.
If it's a symmetry of any local quantum field theory, you could use a notation that looks different, but you're guaranteed by Lorentz invariance that they're going to be equivalent. Notice that it's important to stare at this equation. It's not like psi is invariant under it. So it does something to spinors, but the theory is invariant under it. CPT is not the trivial transformation. It's not a trivial transformations on spinors. That's important. Good. Any questions? Maybe next time when I talk about Weidman axioms, I'll go over a manifestation of CPT over there as well. All right, so we're gonna change gears. This is the end of it for us and spinners for a bit. All right. I think last year I did a better job with spinners. This time I spent so much time on the algebra that I rushed the spinners and it was not very good. I'm not very happy with it, but we have to move on. Life goes on. Causality and propagators. Let's go back to the scalar field. And because we want to have the option of talking about charge, I will often talk about complex scalar field. Often, okay? Sometimes. So far we've talked about locality, symmetry, all of those principles. Now today we're going to talk about causality. We said what causality is, or sometimes people call it microcausality. It's a statement that commutators of observables must vanish outside the light cone. For time-like separated operators, the commutators could be non-zero, but when it's when they are space-like separated, it must be zero. Could it be that commutators are zero even for time-like separated operators? This is a trick question.
Maybe.
Huh?
So the commutation relations equal to zero if they are not in the same time place?
If you have an operator here's space-time. Put an operator here at x. The operator, there's a light cone of x. If they're space-like separated, the commutator must be zero. If they're time-like separated, generically it's not zero. However, there's one important theory for which the commutator is zero, is even when they're time-like separated. Let me guess on what that theory would be. What does it mean to have non-zero commutator? It means that you can send a signal. No, quantum. We're talking commutators. Well, you don't know this in advance. It's unfair to say this. It turns out that if you have only a massless mode, like massless scalar field, the commutators that are non-zero only on the light. Because what is your messenger particle to send a message? It's always moving the speed of light. So here is zero, here's zero. It's only at this point that's non-zero. But that's a very, very unique thing. The moment you talk about masses or generic theories, up here the commutator is expected to be non-zero. The only reason I know that is at some point I was very, very confused about some calculation that was showing that. It turned out that this is something that people used to stress back in the days in quantum field theory, but they no longer teach it. All right, very good. You could actually check that. Yeah. Oh. Whoops. Yeah. Sorry. All right, so here's the commutation relations. And as I said, now these are covariant Heisenberg fields, right? So we're going to be talking in this part, we're going to be talking about Heisenberg picture. We're going to forget about the canonical commutation relations, right? So space-time splitting. We're going to talk about Heisenberg for function phi as a function of time. Causality says that two operators, two observables, the commutator has to vanish if they are space-like separated. All right, so let's calculate the commutator in massive scalar field or complex scalar field. All right, and let's call that this guy, First of all, what is a commutator? A commutator as an operator in free field theory. This is almost a definition. It's proportional to identity. Right? Is that clear why? No? What is a field 5 in terms of A and A dagger? Bunch of A's plus a bunch of A daggers. So if you take two of such expressions, what are the commutators? A bunch of commutators of A and A dagger. What's the commutator of A and A dagger? Proportional to identity. So it will be a function proportional multiplied identity. What is this called? The commutator is called central. It's in the center of the algebra. It commutes with everything. Can you tell why this is very important? Yeah. Well, okay. Whatever. This is essential to get Gaussian correlators, but if you don't see it, we'll get there. So let's call this function delta. What does this function look like? Well, you know exactly what it is. It's, you know how to calculate it. Here is the we calculate this in canonical quantization. This is the covariant measure, and e to the power of minus I k mu x mu minus y mu minus e to k mu x mu y mu. Is it clear what I'm doing? So the commutator has two terms in it. The first term is phi x phi y. It gives you this. The second term with a minus sign, it gives you this. Right? All you need to calculate is the first term, because the second term, you just flip the sign of x mu minus y mu. I put an extra minus sign. Right? Now, why is the 2-point function this thing? Well, do the calculation. You've done the calculation. This is what the 2-point function is. First thing, this is manifestly Lorentz invariant. Can you see it? Why is this expression Lorentz invariant? Well, the measure is explicitly Lorentz invariant. What other things appear in there? K mu and x mu. That's Lorentz invariant. As it should be. You know why? Why is the 2-point function Lorentz invariant?
It depends on the minus, the difference between the two points.
Why is it Lorentz invariant?
Those are contracts.
What is the 2-point function? Vacuum on x, y. Right? Let's apply Lorentz transformation to that. What is the Lorentz transformation here? Lambda x mu lambda mu no x. How does, well, y, sorry. How does this transform?
Bigger.
Right. How does this transform?
Bigger.
What if this were, what if these were not scalar fields? Actually, no, sorry, I don't want to say it's true. What is this? It's not true. This is u phi of x mu u dash. This is u lambda. This is u lambda. What is this? It's u lambda phi of y mu u lambda dagger vacuum vacuum. These are unitaries, they cancel out. For invariance, I should be able to get rid of these two. How do I get rid of these guys?
This action on the vacuum gives it.
Yeah, vacuum is Lorentz invariant. What do you learn? You learn that the 2-point function as a function of y mu minus x mu is the same thing as the 2-point function after applying a Lorentz transformation. So it's Lorentz invariant. Good. The commutator vanishes when x mu minus y mu is space-like. Can you see why? Can you see why this expression vanishes when x mu minus y mu is Lorentz invariant, is space-like? It's a one-liner argument. Phi of x, this is times space. Why does this expression vanish? When they're space-like separated, I can rotate around this axis. This will come all the way here. Well, no, actually, I don't want to say it's a rotation. There is a Lorentz transformation that will send this here, this guy to this point, so that y mu minus x mu picks up a minus sign. There exists such a transformation. It's Lorentz transformation. The expression should be invariant under it. So I'm free to put a minus sign here, which means that the two will cancel. I get 0. There is a Lorentz transformation only when x and y are space-like separated. There is no such a transformation when they're time-like separated. All right. So that's what it is. Good. Let's consider complex scalar field phi and phi dagger, and here is the my commutator. What does it look like? It looks like same thing as before. By the way, sorry, I want to make sure that everybody understands where these come from. Is it clear where these come from? Why is my? Are these clear? Can you see them? What was in the expansion of phi? There was an integral over spatial k, e to the power of I k x a k plus a k dagger e to minus I k x. So I get the minus sign here with a k, for example, and then the plus sign with a k dagger, right? If I time evolve them, how do they evolve? A picks up e to the power of I omega t, sorry, minus I omega t, and a dagger picks up e to the power of I omega t, or vice versa. So you can write them covariantly this way. It's like really 1 or 2 lines of algebra. You repeat that for complex scalar field. What do you find? You find the same expression as before that will vanish when using a Lorentz transformation like this, multiplied by a dagger commutator minus b dagger. These are particle and antiparticle of the complex scalar field. So what do you learn? You learn that causality says to every particle, there must exist an antiparticle. In this context, here, the only way for the commutator to vanish outside the light cone for complex scalar field is that you have the particle and the antiparticle, so that 1 minus 1 is 0. So not only quantum field theory allows for antiparticles, sometimes it says it necessitates them. It says they're mandatory. Sometimes. In this example, we saw that. Any questions? In the remaining time, I'm going to talk a little bit about the aspects, different aspects of this 2-point function for the complex scalar field that I'm going to call D. So D is the 2-point function, phi dagger. What I was calling delta is the commutator, which is D of x mu minus y mu minus D of y mu minus x mu. Good? All right. So it's about 10 minutes. A lot happens here. It's very quick, but a lot happens. And I can, for better or worse, it took many years to grasp, understand what the hell is going on in the next few slides. But hopefully you guys get this faster. But the algebra is very straightforward. All right. Using the mode expansion, this is the expression you can find. I already used it for the commutator. Good? What is the 2-point function where the points are time-like separated? When the points are time-like separated, you can use Lorentz transformations to go and sit in the coordinates where they are equal position, different times. You can always go to that frame. Then the calculation is simple. It becomes this integral, e to minus I omega t. There we go. So this is the integral we're going to do. Because there's no spatial k dependence, I can integrate it this way. This is your integral. And it's a homework problem to see that you could write it this way, but it's a one-liner. I don't really know why it's a homework problem. Because all I've done is changed variable from k to e. No, but there's a part to a homework problem. This integral is still kind of wild. Why is the lower end of this m?
Means stationary local rescue.
No, it's the lowest energy possible, right? What is E? Right? If I'm integrating over k squared, the lowest possible thing is m. Right? So that's the beginning of energy. Such a theory is called gapped. The theory has a gap. Energies don't go all the way down to 0. There's a minimum energy mode. If this was going down all the way to 0, you pick up an infinity. So it's a good thing that there is no 0. Yeah, there will be the evidences. Would you interpret that as a UV or IR divergence? IR divergence. Okay, so part of the homework would be the following. Okay, so you found this expression. Then you can see from this expression that when m times t is much, much larger than 1, long time limit, then you could approximate this integral using the saddle point approximation, and you learn that it scales like e to minus imt. So when you take the 2-point functions, separate them in time by a lot. What is a lot? There's only one scale in the problem, right? 1 over m. So when mt is very, very large, then this just oscillates. The 2-point function oscillates with frequency set by the mass. So this is the behavior of it. Yeah. Anyone? What is a 2-point function? What's a complex 2-point function? As you can interpret. What is this? How would you interpret this as a physicist? Oops, sorry. I think I defined it this way. How would you interpret this as a physicist?
Probability.
Creating a particle there.
Yeah, I see amplitude for a particle to propagate from this moment in time to time t. That amplitude oscillates in time. It's an amplitude. What if they are space-like separated? Well, when they're space-like separated, you could use Lorentz transformation upon Poincare invariance to write them in terms of, to put them equal time and only some distance r apart. Why is it only a function of r? Well, using translations, I get rid of x. It's only a function of x mu minus y mu, right? Using rotations, I learn it's only a function of the proper distance between them. Well, I knew that already, right? From the fact that it's Lorentz invariant. All right, so here's what your integral becomes. In this case, you know how to do the calculation, so I'm not going to bug you with that. And then also a homework problem. You could, after change of variables, write it this way. An integral from 1 to infinity, d of x, this thing. I trust you guys can do it. Similarly, at long distance limit, it becomes like this. By the way, this integral, you could do it explicitly. This is a known function. You will do it explicitly. It becomes like this. So it's m over rq e to minus mr. So it falls off exponentially with mass. Right? Here's an important lesson. 2-point function, space-like separated. In physics, if it falls off exponentially, the coefficient of the exponent is mass. In long distance regime, if you have a gap in your Hamiltonian, 2-point function will always fall off exponentially with an exponent that is the mass. If you don't have a mass, it cannot fall off exponentially. Why? Dimensional analysis, right? By dimensional analysis, you could not have what's in an exponent must be dimensionless. If you don't have a mass, what are you going to put next to r? Right? So what can it do? What are the physical options that are left? If exponential decays out, what's left? Can it be constant? There was a suggestion it could be constant. Can it be constant, or does that violate the principle? It does violate it. Huh?
It should be zero.
It should be zero. Why? Actually, very good, very good. Why should it be zero?
Well, I'm thinking of the light cone.
No, like in words. Can you say the word? Correlations should fall off. Why? Is there a name for that? There's something that this is something you can prove by the way quantum field theory, but in an extended quantum system, is sanity. and we use it all the time. Clustering. Clustering says if I have a bunch of operators here in space, I start separating them in space. In the limit of infinite, separating infinitely, the correlator should cluster. What does that mean? It means that the correlation function of this should be correlation function of this times the correlation function of this. There should be no connected piece to the correlator. In between, I can put n vacuum. Right? This is called clustering. It's an intuition you should always keep with you everywhere you go.
That's equivalent to getting to be able to separate probabilities. We have conditional independent probabilities.
You could say, yeah, it's related to that, but it's basically the same as that they become independent. Right? Sorry, I'm running out of time. I just want to make one more thing. I just want to finish the thought. So when there is no M, what is the behavior? What can it be? Said differently, could you have guessed square root m over r cubed? E to minus mr from basic physics you could have guessed. Could you have guessed the other part? The answer is yes. Why? Because of physics, you should be able to come up with these or carry these intuitions around. What are we calculating? This. Is this dimension full? Dimensional full quantity. Dimensional analysis. What's the dimensionality of this? Yeah, it is dimension full. What is the dimensionality of field phi? How would you read it? How would you describe to me what the dimensionality is? I can write it on the board, but like, what's the dimensionality of it? No. Okay. So what is the action? Del mu phi squared minus a half. This is action, right?
I can assume the length.
Yeah, you could figure out the dimensionality by this. You're going to exponentiate the action, right? So this is dimensionless in units where h bar is equal to 1. So what's the dimensionality of this? This is an interval over space-time, has dimension d plus 1. So this has dimension minus d plus 1, right? There are two derivatives. That knocks off two powers. The dimensionality of phi is going to be d minus 1 over 2. Good? So the dimensionality of this is d minus 1. We have to construct an object that has dimensionality of d minus 1 over there. If you push this dimensional analysis a little bit further, you'll land on, without the 3 to 2 pi something, you'll land on the correct dimensional analysis. Okay, I'm running out of time. I just want to say one more thing. I didn't get to the contours. Just to finish the thought, if you are in a theory with no masses, what are the possibilities for the decay, for a function that decays and is not decaying exponentially? What other things can you imagine? That doesn't happen. That's discontinuity. This requires discontinuity. What other things do you guys know that decays? Besides exponents. You do know something. Come on. 1 over r, exactly. Or 1 over r to some power. Otherwise known as the power law. So if I don't have a mass scale here, right? And I want to write something that has dimensionality of d minus 1. What can I write? 1 over r to the whatever the hell the power is that the dimensional analysis tells me. This is the only option. This is absolutely the only option. This is called conformal symmetry, conformal invariance. In a conformal theory, correlators decay parallel, like parallel, the connected piece of the correlator. In a massive theory, they decay exponentially fast. In principle, there is a mixture of both, but of course the exponent is the one that's visible physically.
I was gonna say, I can see why it's scale invariant, but how does that also apply to formula?
Oh, no, I haven't told you any of that.
Okay.
Yeah, but this is just like, in conformal invariant theory, this is what it is.
Okay.
All right? Okay, so we're out of time. I just want to summarize this way that keep this in mind always. 2-point function in time should oscillate at late time with frequency set by the mass. In space, if you don't have masses, it decays parallel. If you have masses, it decays exponentially fast. Okay? Think about what you expect the behavior in time would be when you don't have masses. Thank you.